Okay, so the next world we're looking at to illustrate the machine evolution is a genetic algorithm search to write the first line of Finnegan's Wake by James Joyce. Now, the first line of Finnegan's Wake is a bit strange. It's like this. And that's our goal, if you like. And the fitness of our solutions, which all start out random, they're already looking very non-random, but they did actually start out random. Why don't we reload? And you can see they start random. They're entirely random sentences, but they're given a score of how close they are to the goal, and then the fitness is based on that score. So you can look in the code to see the relationship between the score and the fitness. So the fitness isn't simply the number of characters that they have correct, because then the fitness of all of them would be almost identical, especially here towards the end. It would be almost impossible to tell the difference between the fitness of ones that had one character out and ones that had two characters out. So there are 66 characters in the first line of Finnegan's Wake. The score is how many you have right. And one of our solutions has reached the maximum, which is 66. There it is there, which is number 49 out of 99. Well, they start at 0, so there's 100 of them. So in that fairly short time, we found a perfect solution. Now, we were helped along the way by having this score as to how well we were doing. That's the crucial thing. So we weren't told the answer. We weren't told what the actual solution was. We were just told how good our sentence was. So at the end, when we found the solution, most of the population aren't bad. They've got about 60 characters right or more. At the start, the number right is tiny, but look how quickly it grows to 30, 40, and 50, and fairly soon we'll see lines that have 60 characters right. So what's going on here? We're not being told the correct answer exactly. We're being told a distance from the correct answer, or if you like, we're being told a fitness function. So the score is the number of characters correct. The fitness is based on the score, but it isn't exactly the score, because otherwise evolution would regard all of these as more or less equal. And it wouldn't be focusing on the 65s and leaving out the 63s, which of course is what it should be doing. So when we actually finish, we found the goal string in this case after 665 generations. So that means we looked at 665 multiplied by 100 strings of text, which seems like a lot. But if you did a random search to be sure that you'd found all of the possible sentences, well, that would be 95 to the power of 66 in order to guarantee that you would find the correct sentence. So this is absolutely miniature compared to the random search. Now, there's a fundamental thing here, though, which may make you not so impressed by this, which is that we actually know the answer. So we actually know what we're searching for. We know that we're searching for the first line of Finnegan's Wake, but we know the first line of Finnegan's Wake. So what's the point of a genetic algorithm? There's no point at all. So the point of doing an example like this with a known solution is to see how the genetic algorithm works, how it makes progress generation after generation as it gets better and better results, to be able to draw it, map it, debug it, and so on. But the genetic algorithm is meant to be used on problems where you actually don't know the answer that you're looking for. And the answers that the genetic algorithm comes up with are new. They're things you never imagined. And we'll be seeing those in another world. So we can run this world without having done much of the machine evolution theory. We can also clone it, edit our clone, and there are some changes that we can make. So if you look at the exercise after this video, we can change a few things here without having done the machine evolution theory in detail. An obvious thing you can change is the target sentence. So you can go and change that. You can change the speed of it. So if I search for frame rate. There's the speed of it. Yeah, that's a P5 thing. And if you slow that down, you can see much easier how well it's working. You can also try your hand at some of the other constants up at the top and see what happens. But some of these things we'll have to wait for later when we examine the theory behind them. Now, if I run this and open up the console, at the moment you'll see that there's very little in the way of, there's no debug information, in fact, going on in the console. If you go into the code, and of course you've cloned it, you've edited it, you've got your own version, you can turn these constants on or off, and when you turn them on or off, or when you turn them on, you'll get debug information about different things that are going on in the console. So you can see how mutation is working, you can see how crossover is working, you can see how reproduction is working. So try that, experiment with the debug information as part of seeing how the entire system works, how it makes new individuals, how it decides their fitness, how it picks individuals for mating into the next generation. The next thing that you want to change is to get to work on some of these constants up at the top. So the population size is 100. Well, what if we made it 100 million? Is that better? Well, maybe the system can't cope with that. How about 1 million? Surely that's good. Or is it? Because if it's 1 million, the first 1 million are going to be random. So it's going to spend ages working with 1 million random solutions. It's going to be wasting loads of time looking at rubbish solutions. So just making population size huge isn't necessarily the answer to making a better search. We could just waste loads of time. The mutation rate, the number of times in reproduction, well, go and have a look, see when mutations happen. Mutations happen at a regular rate, and should there be more or less mutations? Change it to 1. What does that do? So answer in the comments perhaps, or have a discussion. Is that a good idea? Mutation rate 1? Does that sound right to you? How about mutation rate 0? What would that do? Or mutation rate 0.1. So is there a perfect mutation rate? Another one here is the relationship between fitness and score. So earlier we said that the score is how many characters the string has right. But if that's the fitness, you get a very strange search where basically they all kind of look the same fitness. And it doesn't really focus on the fitter ones, which is what it should be doing, and dropping the less fit ones because they're all more or less the same. So the idea of this power-based thing is to let it focus more on the very fittest. And the bigger you make this, the more it focuses on only the very fittest reproducing and dropping off anybody apart from the top one or the very top tier. So make power base 100. What happens? What happens to our search? Is that a good idea? Is the point? Or, should power base just be huge? What happens if you make it 1? So change these things. Put power base up, power base down, population size up or down, and see does it make for a better search or a worse search. So it's quite easy to make the search worse, and by moving these too far in either direction. So it's an empirical problem to figure out what a good heuristic is in order to search this space in a reasonable time that's available to you. All right, there's a few other things in the exercise, as you'll see when you go on to the exercise. One of them is there's always crossover. How about if you change it to just having a probability of crossover? So the crossover sometimes happens, sometimes doesn't. And what that would mean is sometimes you get clones of the parents and sometimes you get new individuals that are a mix of two parents. So is that good or bad? But make it customizable so that the probability of crossover can be between 0 and 1, and then look at it at 0, look at it at 1. See how the search progresses. The probability of mutation is another one. We have probability of mutation built in. But one thing you could do to change it is to make the mutation high at the start and lower later on. So the thinking is at the start all the solutions are rubbish, so we want to change them drastically, they're all random. But as we go along, we don't really want massive mutations because we want to focus on what's good about our solution to have survived this far and make small mutations to look for something slightly better. So a general good strategy is to have high changes when you don't know much, and later on when you want to keep alive some good solutions, smaller changes, smaller mutations. So do that, make probability mutation change as time goes on. Another one which is nice is to make this a much larger block of text and see how the thing goes. Is it just impossible to do the first page of Finnegan's Wake, for example? Or can you find some combination of parameters that can do that in 5 minutes?